In the last video, we deduced n plus 1 equations del z over del w1, del z over del w2, del z over del wn, and also del z over del b. So our objective is to compress all those n equations for del z over del w1, del z over del w2, del z over del wn in a single equation using matrix multiplication to express all those equations into a single vectorized equation. So here we derived del z over del w1 is equal to summation I is equal to 1 to m del z over del zi times xi, and 1 is here for this w1. And similarly, del z over del w2 we had summation I is equal to 1 to m del z over del zi times x2i, and similarly for del z over del wn is equal to summation I is equal to 1 to m del z over del zi times xni. So we had this equation. Now we can also write this one as del z over del z1 times x1 plus del z over del z2 times x2 plus so on, plus del z over del z m times xm. Similarly, for del z over del w2 also we can write likewise. Why I'm writing? Because we can think of as a matrix multiplication of one vector with the matrix, which we are gonna discuss now. Del z over this as del z over del z 1 times x1 plus del z over del z2 times x2 plus so on, del z over del zm times xm, and 2 here for this 2 subscript. And now if we expand this one, we'll be getting del z over del z1 times x1 plus del z over del z2 times x2. I know it's boring to write all those equations, but I'm showing you something here, and it becomes del z over del zm times x m here, and the subscript is n. Now, so now what exactly is this thing? We can think of this term as the row vector multiplied with a column vector, right? If we define a row vector del z over del z1, del z over del z2, del z over del zm, because all those row vectors appear in del z over del w2, del z over del wn also. So we can write these equations as del z over del z1, del z over del z2, writing it in a row vector, del z over del zm. And this is the trick, by the way, to express all those in a matrix multiplication form. So this is a row vector of dimension 1 into m. And what is this quantity? x1, x2, xm, x1, x2, xm, and here subscript 1, 1, 1, 2, 2, 2. So we can think of this row vector multiplied with a column vector, right? So our first column vector is this one, this term. So basically this is x1, x2, and this, oops, sorry, this is also x1 here, because x1 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 appears here. This is x1, and this is the first training sample. So x1 1 is nothing but the first feature of the first training example x1, because this subscript stands for the for ith feature, right? So first feature here for the second training example, and first feature for the mth training example, first feature. And when we multiply this column vector with this row vector with this column vector, we'll get this equation, right? So stacking all those column vectors, we will be getting this one, right? So this is the second equation, x2 x2 x2. And this is a trick here, by the way, and this trick we must explore. This is x1 x2 xm. And for the nth training example, we have xn, xn, and xn. First training example, second training example, sorry, and the mth training example we have. So this is all about compressing n equations into this form, right? So we will be getting this as, we can write as this basically, this is 1 times m, the dimension of is 1 times m. And what is this dimension? And the dimension of this as, this is 1 1, and we can see that m rows are here, so m times n. So 1 times m, m times n, when we multiply it, we'll be getting 1 times n here. So this can be thought of as del j over del w1, the first entry of this vector, because this will give 1 times n vector, and del j over del w2 for this row vector with the multiplication of this column vector, and all the way up to del j over del wn. So we have 1 times n, this is the dimension of this vector. And by the way, this is nothing but the gradient vector, right? So we can also write this as del gradient of the cost function j, and this gradient is del w. I'm writing this way. This is how we express the notation of gradient, right? And this gradient is equal to, what is this? This is a row vector, right? So this row vector can be written as this is basically the gradient of j with respect to z1, right? So, or maybe we can express like this way: del j over del z vector. This is the notation I'm using here. Times, what is this quantity? This is a matrix, right? And if we look at our design matrix, the input matrix, we can see that the row is transposed into column here, right? So all those rows, because in design matrix we have x1 x2 all the way up to xn. And first training example, all the in the first column there is a first training example. So we can see that if we transpose this one into a column, we'll be getting the same thing, right? So basically the entire matrix is nothing but transpose of the design matrix. So this quantity, this quantity, this matrix is nothing but the transpose of the design matrix xt. So del z over del z times the transpose of the design matrix xt here. So basically this is a single equation we can compress. This is a single equation we can compress all those equations into this one, right? So basically we have this equation, and in the next video we will see that we can implement multivariate linear regression using this equation for the back propagation. And this is the first equation we can say, and the second equation for del z over del b we have already found, and there is no need of vectorization for that because that is itself a single equation. So we have del z over del b as nothing but del z over del z1 plus del z over del z2 plus so on del z over del b, del z over del z1 plus del z over del z2 plus so on plus del z over del zm. And by the way, this is nothing but sum of all the elements of this vector, right? Del z over del z1, del z over del z2, del z over del zm. This is a vector, row vector del z over del z vector, right? So this is nothing but the sum of this row vector. So sum of all those elements of del z over del z vector. So this is the second equation for the update of del z over del b, for the update of b. So this is the gradient for b and this is the gradient for the weight vectors, right? So using these two equations we can update w1, w2, wn and also b using gradient descent, right? Like this way. W, we have the w vector, so w vector is updated as w vector minus the gradient of j with respect to w vector. So the gradient of j is this one which we already calculated using this equation. So del j with respect to what? With respect to this w. So this is the gradient descent equation for the update of w vector. And similarly for bias b, we have this update. B is updated as b minus this equation. This is the second equation we have, del j over del b, which is expressed as sum of all the elements of this row vector del z over del z vector. So b is updated as b minus alpha, oops, alpha is also here, alpha is the learning rate, b minus alpha times del z over del b. So this is the gradient descent equation for the update of w1, w2, wn using this and also the p. So we can see that only two equations are necessary for the update of weights and bias, not n plus 1 equations, because n equations have been compressed into this single equation, and for the bias we have. So in the next video we will see about the algorithm for the multivariate linear regression, and also we will implement that algorithm in Python right from the scratch. Fine, thank you.